giant laser measurement systems and ripples in the fabric of space and time, which we're going to talk about all this morning. I'm Dr. Brian Lantz. I'm part of the LIGO scientific collaboration. I work at a project called LIGO. Here's the two LIGO facilities. Here's one in Louisiana. Here's one in Washington State. LIGO is the Laser Interferometer Gravitational Wave Observatory. I brought a laser interferometer. We'll talk about that. I'll tell you what gravitational waves are, and I'll tell you the thing that we observed. The group I work with is enormous. There are like 1,000 people. We wrote a paper, right? The paper came out on February 11th with this cool discovery. There were 1,004 people listed as authors on this paper from all over the world. Here's Stanford right here. You can kind of see us. Kind of a shout out to the locals. And we're funded by the National Science Foundation. I forgot to say that at my last talk. I'm probably going to get a hard time for it. All right, so LIGO has two facilities running right now. One's in Washington State, one's in Louisiana. There's a French-Italian collaboration called Virgo. They've got a big detector near the Leaning Tower of Pisa. There's a bunch of Germans and Scots who have a detector in northern Germany. The Japanese are building one underground in Japan. We've recently entered an agreement with the Indian government to put a LIGO facility in India as a collaborative work with the Indians. And the Australians have a detector in the corner of a detector in Australia. So this big network of detectors. And on September 14th, 2015, the two US facilities were up and running, and we saw this signal come in. This is the strain, which I'll tell you about, as a function of time. So about 200 milliseconds, there's this signal. And at the beginning, the signal's all noise. You see the LIGO, the Hanford signal and the Livingston signal kind of look like junk. But right here, there's this big chirp on the data. And the chirp here and the chirp here match. We've got them lined up. They're off by about 7 milliseconds, which has to do with the light travel time between the two facilities. There's noise, there's signal. That signal came when two black holes, 1.3 billion light years away, crashed into each other. So here's a little animation of that. I'm going to turn off the rest of the lights and see it. So here we've got the two black holes. These are about 30 times the mass of the sun. I hear you guys are studying black holes in your gravity class. And behind them is just a field of stars. And these black holes are going to start circling around each other in a second. And what you're going to see is that the gravity of the black holes is acting like a lens, and it's distorting the field behind it. So as they start orbiting around each other, it looks like space is getting really distorted. And it is, and the biggest effect is that your view of the stars behind it are getting twisted up by the gravity of those two black holes. And they're orbiting into each other like the Earth and the Moon, except they're about to crash into each other. We slow the time down, and right here they're going to merge, and if you look out here, you see the whole field behind is getting all distorted as the waves of gravity travel out. Here's the same thing done with fancy supercomputers, showing another version of it. I'll walk over here so I can point to some stuff. So here you got your two black holes. These are 29 and 36 times the mass of the sun. This field represents space-time. It cut through space-time, and the colors represent how time is slowing down. So underneath these, you can see there's this big gravity well, and time's running really slowly under there. These two black holes are coming in for about 0.3 seconds from when they're going to crash into each other. And this looks like what you'll see here on my rubber universe in a minute, right now. And as they're coming in, now you see the space is getting very distorted. If you look down into these little red holes, sometimes you can see the black edge, the event horizon, the edge of that black hole. And here the space is getting very distorted. Here we can see our waveform. Oh, peak of the waveform. We stop it. They become a single black hole. And then you can see these waves radiating out. That's what we saw. That's the thing that we saw. We got to end up with a single black hole at the end, which is spinning very, very fast. All right. Some people who made that video for us. So gravity. You guys are studying gravity. Here's probably the rock star of classic gravity, Isaac Newton. He said that gravity is like a force between two objects, proportional to g, the mass of the two objects, the distance between them. So you got something like the Earth, you got the apple, the apple can orbit around the Earth if it's going fast enough, and there's like this stage, these two objects on it exerting a force on each other. So it's a great theory, explains a lot of stuff. You can do a lot of classical mechanics with it, orbits, rockets, all kind of cool stuff. But there's some problems with this theory. One of them is, for instance, let's say you had this apple, it's got some gravitational field, and then you picked it up and you walked over here with your apple. Right? The gravitational field of the apple is going to move along with the apple. And if you believe this formula, what they would say is that all across the universe, the gravitational field of that apple is going to change instantaneously all across the universe. Right? That's got to be wrong. It's got to be wrong. So this was a puzzle for gravity for a long time. It was resolved when Albert Einstein came up with the general theory of relativity. And he said, look, space is not like a big stage with objects on it. Space is like a big field. And the masses distort the field. So I brought along a little rubber universe here, right? So you got your Earth, right? It's heavy. You put it on the field and it distorts it. You guys see that? You guys in the back see that? Stand up if you want, it's okay with me. And then it's not the force of this object that pulls the moon along. It's the distortion of the field that does it. Right? And so as you put objects in the field distorts, and the distortion of the field is the thing that causes the objects, tells the objects what to do. Not only that, but there are these, since you got this field, you can have traveling waves in the field. You got like a pool of water, right? You put a rock in the water, right? The whole lake doesn't go up instantaneously. Instead, you get waves that travel out across the surface of the water. And those waves in the water are like the waves in the gravity field that we're trying to measure. Let's look at this video one more time, just because it's cool, really. But if you look, so here you can see those distortions in the bottom of these gravity wells. But what I want you to do now is watch the colors out here as these two objects collide. And what you can see is that the distortions are going to travel out as these colors. See that? See those distortions traveling out? So those are the gravity waves, the gravitational waves, being formed by this event. And that's what we're trying to measure. And if we can measure those waves, then it'll tell us something about the black holes. So when the waves get to us, so that object was 1.3 billion light years away. When the waves get to us, of course, they're much weaker. And they distort space in a very strange way. What happens, you got your two black holes, they're crashing into each other. You got some waves coming off. If you have a ring of particles in space, as the wave comes through, the ring is going to get distorted into an ellipse. And it oscillates back and forth like this. Not because the objects are moving, but because the space is stretching. Which is really weird, right? So if Mr. Who were to suddenly, like his head would suddenly blow up like a supernova, right? Big core collapse, all kind of mass, the center of that supernova collapsing, huge gravitational waves come off. As those waves came through me, right, I get stretched in one direction, and compressed in the other, and then back and forth like this, and do sort of like the stickman dance, right? As the waves came traveling through. So if you want to measure something like that, how can you do it? There are a couple of ways that people have thought about. What we decided to do was to build a big laser measurement system. So you have a laser comes in, you got a beam splitter, and you got these two arms, right? So as the wave comes along, one arm's going to get longer, and one arm's going to get shorter, and they oscillate back and forth like this. And this laser measurement system is called an interferometer because it measures the interference of light here at the beam splitter. Interferometers are very good at measuring length changes. This interferometer, the arms are 2.5 miles long. Why is that? The strain, so the gravitational waves, they produce this stretching of space. We describe that as a strain. So it's a proportional stretching. So if you have something that's a meter long, that's a 10% strain, then it gets longer by 10 centimeters. The gravitational wave we measured had a strain, a relative stretching space of 10 to the minus 21. It's like that. It's super, super tiny, right? And that's because space gets stretched, right? Space is really stiff. It does not like to be stretched. You can put a tremendous amount of energy into a gravitational wave, and it stretches space just the tiniest amount. So if we want to measure a strain from a gravitational wave, we need a big machine. In fact, when Einstein first wrote down general relativity in 1950 and then gravitational waves in 1916, he figured no one would ever be able to see gravitational waves. And for like 100 years, he was right. Okay. But we did finally measure them because we got a lot of fascinating new technology. And he didn't know about black holes. So we've got this big laser measurement system. We're trying to measure a strain of 10 to the minus 21. So how big is that? Right? How big is that? For us, it's 4 10 to the minus 18 meters, which is a number so small you can't really get your head around it. But if you took the distance from the Earth to the sun, and you applied a strain of 10 to the minus 21, you can work out how big that is. It's about the size of an atom. So what we saw was a little ripple in the length, equivalent to changing the distance from the Earth to the sun by the size of an atom. And we measured that with pretty good signal to noise. All right, so the interferometer, which is this laser measurement system, let's give you a quick demo of how that works. So here's our laser. Beam of light comes out of the laser, hits the beam splitter, splits, comes back together, and as the two arms change their length, you get some light that comes out here onto your detector. And that works because the light is really an electric field. You see the yellow part of the field comes along here. This is the amplitude of that electric field. It bounces off the mirror, comes back. The electric field from the other one is drawn in blue. They come back together to the beam splitter, and they add up. And here you can see that they're out of phase. So the positive of one lines up with the negative of the other, and so they add up to 0. There's no electric field, there's no light. But as you change the length, you change the phase of these two electric fields, and when they line up, you get a lot of electric field and you get power. When they don't line up, you get no electric field and you get no power. And so you can measure the light here, and that tells you about how the length of the arms is changing. And now you've got something with a 4-kilometer long arm and a ruler, and the ticks on that ruler are the wavelength of light. So for us, it's about a micron. And I brought along one of these things to kind of give you a feel for how this works, this little home interferometer. And what we're going to do is we're going to try and bend this steel beam. So let's get somebody like Mr. Hu. Come here for a second. So here we have a steel bar, and Mr. Hu is going to try to bend this steel bar for us. We don't think we're going to have very much success because it's really quite a stiff steel bar. So we need, yeah, that's right. So we need someone who's really strong. How about you? Why don't you come up here, give me a hand here for a second. What's your name? Sandy? Xanthi? Xanthi, all right. Great. I'm going to turn off the screen here if I can find the right button. All right. And I brought along a laser interferometer. Here, step back just there. Don't jump on before. So here we got a laser. We got our, here's our laser. Here's our, that's not bright enough to hurt you, but still. So the beam comes here, comes to our beam splitter. Part of the light goes down this way. Part of the light goes down this way. They come to these mirrors mounted on these big steel beams. They come back together to the beam splitter, and there's a spot right there on the wall. The intensity of that spot is related to the length of these two arms. And we're going to see if Xanthi can bend this steel beam enough to change that spot. So come here. I want you to push on the beam. Oh, no, wait. Just use your pinky. Just use your pinky and push on the end of that beam. See if you can change the spot. There we go. See? Mr. Cruz got nothing. Isn't that cool? So she's able to bend this steel beam with her pinky enough that our laser measurement can totally see that. Thank you. Give her a hand. All right. So that's what we've got. Ours is very much like this, except that the one in LIGO, the arms are 2.5 miles long. So take a little dive into history for a moment. Michelson interferometer was invented by this guy right here, Albert Michelson, back in 1887. And there's a funny history to this because Michelson and Morley were trying to use this interferometer to measure what happens when light travels along. And they figured, at that time, in the 1880s, people thought light had to travel through something, which makes sense, right? Water waves travel through water, sound waves are compression waves in the air, earthquakes shake the ground. Light must travel through something, right? Turns out it's not true. They thought it traveled through something called the luminiferous ether, which is a great phrase. And so they built an interferometer right here to measure that. So here's our light source. They used an oil lamp. Here's our beam splitter. Bounce light back and forth here to E, and then back to the beam splitter, and then back to here, and back to the beam splitter. And then they look at it with a little telescope. And what they figured was that they should be able to see the light being different as we traveled along. Because if the light is going to travel through something, if you're still with respect to the light, like our water bug here, the light travels through this luminiferous ether kind of in the same way in all directions. But if you're like the duck, and you're moving along through the ether, the waves here aren't the same. The duck can see that the waves in front and the waves to the side are different. And the Earth is traveling around the sun at, anybody remember? I looked this up last night, 67,000 miles an hour. Right, we're whipping around the sun. So we should be like the duck. And we should be able to see that the light in the two directions and that interferometer is different, right? So when the arm in front is lined up, it should be one way. And then they did this really clever thing. They put their whole interferometer on a 5-foot square block of rock. They floated it in a pool of mercury so you could turn that interferometer. So at some point, the arm in front is lined up with your 67,000 miles an hour. And then you turn it along, and now the right arm is lined up. And then you keep going, and now the left arm is lined up. And so you can watch the change in the light as you go whizzing through space. And what they saw was this. The dashed line is the level of the prediction divided by 8, and the solid line is what they actually measured. They didn't measure any luminiferous ether. In fact, Michelson wrote a letter to his friends like, there is not any luminiferous ether. We can't measure it. But there's still a problem, right? How does this work, right? Why is it that an interferometer sitting still and an interferometer traveling at 67,000 miles an hour around the sun act the same way? That's kind of weird, right? Albert Einstein said in 1905 with his special relativity, he resolved the problem. He said, look, it's not like that. There isn't any luminiferous ether. The speed of light is constant. For any two observers whizzing past each other, the thing that's changing is not the relative speed of light. The thing that's changing is space and time. Right? It's your perception of space and time that is relative. This is his special theory of relativity, and that is weird. 9 years later, he came up with a special relativity, his theory of general relativity, and then this prediction of gravitational waves that comes out of this relativity. And the cool thing for me is that now, 100 years after that, we finally measured his gravitational waves with our Michelson interferometer. So a nice little closed loop there. Now, as I said, gravitational waves are hard to measure. Space doesn't like to stretch. We've been looking for them for 100 years. We've got this giant machine. There are 3 things that we do with this machine so that we have some hope of measuring these tiny distortions. One, we have really long arms. So if you've got a relative stretching of space, the longer the space is, the more absolute stretching you get. So we got arms that were as long as we could afford, 4 kilometers long. The second thing we do, here's another version of that interferometer, I put some more of the mirrors in, is we measure the distance between these mirrors very, very accurately. One thing we do for that, I can talk about this for hours, but I won't. As we bounce the light back and forth in this arm, we don't just go to the beam splitter, we don't just go from the beam splitter to the end and back, we actually bounce it back and forth between these 2 mirrors about 300 times. And then we bring the light back to the beam splitter. And then when we interfere it, it turns out, you get to this in college, the precision with which you can measure those phases, the things that lined up or didn't line up that caused power to come out here or not to come out here, the precision with which you can measure that is limited by your counting of the photons. It's limited by quantum mechanics. And the more photons you have, the better. So another thing we do to very accurately measure the distance, we have a big laser. So here's a picture of our big, scary laser. This was a contribution to the project from the German government. Here you can see 3 of the German scientists. I have no idea who's actually behind these laser safety goggles. This is the world's largest ultra-high performance laser. See, it's all, you can't actually see what's going on in here. It's just kind of a cool picture. And then we end up with almost 100 kilowatts of light circulating in these arms right now. We plan to go up to over 750 kilowatts circulating in those arms. So we've got really long arms. We can measure the distance of the arms very accurately. The third thing we do is we try to hold the mirrors very still. Because if the mirrors are shaking around, then the length of the arms, of course, is changing. That's no good, right? No one wants to measure trucks. You want to measure gravitational waves. So if we, let me go back a second. The first thing we do to keep these mirrors really quiet is we pump all of the air out of these long arms, and we put this into a big vacuum chamber. And here's that vacuum chamber. To get a scale for that, see these little blue posts out here in this gray chamber? These posts are 8 feet tall. Top of that chamber is 18 feet off the ground. And if you cut it open, you can see that gray chamber, the blue posts. The optic is sitting inside. There's a 4-stage pendulum at 10 hertz, at 10 cycles a second. Right? That optic is moving 1 billion times less than the ground is. Part of the thing I work on is making that true. So you got the laser beam, it bounces off this optic, bounces back. Here's another drawing of that optic. Here you can see that optic, it's 34 centimeters in diameter, it's 20 centimeters thick. It weighs 40 kilograms, about 90 pounds. And it's suspended as a 4-stage pendulum. Here's my last demo. Nope, I lost it. There it is. So, I brought along for you to see an exact scale replica of the advanced LIGO optic, as you can see right here. And I've hung it from a suspension to demonstrate why suspension is so useful, right? So if you move our suspension point at low frequencies, the optic just kind of follows along, right? I can see your eyes are getting very sleepy. If you move the top at the resonance, what you see is that the mirror moves a lot more. And so we build active controls all around the whole suspension system to control the resonant motion. But the good thing about a suspension is that if you move the suspension point faster than the resonance, you can move the top a lot, and the mirror just doesn't keep up because you get isolation from your suspension system. And that works both vertically, if you have some kind of a spring, and horizontally. Right? We have a 4-stage pendulum because obviously if some is good, then more is better. Let's see if I can make this work. So here I brought a 2-stage suspension. And so now I should be able to move the top rather a lot. I'm moving pretty fast and kind of pretty high motion. And what you can see is that if you look at my hand is really moving a lot. It's moving a lot more than the optic is. Right? And so by stacking up 4 stages like that, you can get this mirror to move much, much less than the ground does. Here's a scale of how big that thing is. This is an engineering prototype up at Hanford with Betsy, who's our lead suspensions guru up at this facility up at Hanford for scale. You can see this thing is big, right? It's taller than I am. Here's the engineering version of the optic. It's just a piece of metal. The real optic looks like this, which I just threw in because it's a pretty picture. These optics are about $1 million, so they deserve a little bit of face time in the presentation. These optics move 1 billion times less than the ground does at 10 hertz. They're hanging off of these big table contraptions. There's an optics table right there. It looks like this, except doesn't have any paint on it. And this is the thing that I work on. And this table, at 1 hertz, at sort of 1 cycle a second, moves 1,000 times less than the ground does. And you can control where it's pointing with your computer control system. Here's some guys installing that thing up at the site in their clean room suits. Mostly, when I look at this, I see all kind of issues with it. You just see a bunch of shiny metal, but it's a pretty picture. And so now you've got the 3 things that you need to make this measurement work, right? You've got long arms. You've got a really good way to measure the distance between the mirrors at the end of your arms, and you've got really quiet mirrors. So now what you do is you wait. Right? You just wait. And you wait for something unusual to happen at both sites. So I've got here, this is called a spectrogram. So it's about half a second worth of data. And then there's a color representing the intensity at each of these frequencies. So here we got low frequencies. Here we have kind of 250 hertz for band people. You know that's still pretty low. And this is the signal that we saw. You can recognize that waveform right there. It's a strain of 10 to the minus 21. So when you start to hear something that sounds like this, let's see if our audio works. So it's sort of a band-passed version of the output of the interferometer, that the light that's going on in that detector, you just play it through your speaker. Just kind of a low rumbling, sort of the background noise of the detector. Then, in the middle of the night on September 14th, about 45 minutes after a bunch of the graduate students had gone home, because they're like, we're done for the night, we're going home, we're leaving it running. The observing run's not supposed to start for another week. We're about ready to go. We'll just flip the machine on to run and go get some sleep. This is what happened. Play it again. There, I've shifted it up so you can hear it a little better. Right, so two versions at low frequency where it actually came in, two versions kind of shifted up so you could hear it a little better. Right? That's the thing that we saw, 200 milliseconds. All the stuff's over 200 milliseconds. You can do some data processing on this. Here's sort of the best reconstructed numerical waveform for the two black holes spinning in, crashing into each other and becoming a single black hole. 29, 36 times the mass of the sun. This is a couple of things. Most of us weren't expecting this. Kip Thorne, who was one of the theory people behind the instrument and the guy behind the idea for Interstellar, he said the first thing you're going to see are black holes because they're just so big. But we're like, but Kip, how many are there? Nobody else knew either. Nobody else knew. It's the first time we'd ever seen a black hole bigger than 25 times the mass. That's not 25 solar masses. In the range between 25 and like 1 billion solar masses. We know that there are giant black holes in the middle of the galaxy, right? But for this size black hole, it's the first time anyone ever seen one. It's also the first time anyone had ever seen two black holes in a binary system, spiraling around each other. So that's two firsts. One of the interesting things about this is that the two solar masses are 29 and 36 solar masses times the mass of the sun. The final black hole was 62 solar masses. Anybody see anything weird about that? 3 solar masses have vanished. Right, it went from 65 to 62. And that's because, remember, E equals mc squared. Einstein tells us E equals mc squared. 3 solar masses worth of energy were emitted from this system in 200 milliseconds. Which means that for a few milliseconds right in here, there was more power coming off of this system. There was actually 50 times more power coming off of this system than there was in all of the light coming off of all of the stars in the visible universe. That's how much power was coming off of this thing. And yet, when the signal got to us, it was so small that it took this huge machine to actually see it. You can look at the speed of the two black holes as they run around each other. There's this green curve right here. This is the velocity. It's a function of c. 0.3, 0.4, 0.5, 0.6 times the speed of light. So you've got these things that are 30 solar masses. They're a couple hundred kilometers apart. So here to Sacramento, they're switching places 75 times a second, going 3/4 of the speed of light. It's a pretty bad place to be. Anyway, so we finally measured one. You might think, well, that's the end. You guys have succeeded. Congratulations. But we actually think of this as the beginning. And one of the neat things about doing astronomy is that you can start doing astronomy very easily, right? You walk outside, and you look up at the sky when it's dark. Or you come to the astronomy night here a couple of weeks ago, and you look at the sky with a telescope. And what you'll see is something that looks like this. This is the Milky Way. There's the center of there's the center of our galaxy. It's kind of occluded by dust, and there's stars around all throughout the rest of the universe. But this is the brightest thing that you can see. But when you look at the sky with different instruments, you see all kinds of different things, right? So this is a picture of the sky. The same sky is seen by the Fermi telescope, run by folks up at SLAC. And you can see there's the center of the galaxy, nice and bright, but there's all this stuff over here, there's weird flashes over here. The first time people put a gamma ray telescope up in space, actually, it was the US military who did it, and they were watching for gamma rays from Russian nuclear explosions. And the thing they saw was, in fact, they did see flashes of gamma rays, but they were coming from outer space, and they're like, maybe the Russians, I'm not making this up, maybe the Russians are setting off nuclear bombs behind the moon? Now, in fact, there are these weird gamma ray bursts. The actual explanation is even weirder than that. They actually think that it's two neutron stars, which are 1.4 times the mass of the sun, made of stuff that's the density of the nucleus of an atom, crashing into each other, and those things crashing into each other, which is a great source for LIGO, right? When those two dense matter objects crash into each other, they emit huge bursts of energy. And we actually think that's what the gamma ray bursts are from. So you can also look at the sky with an infrared telescope. This is the FIRAS telescope, and here you can see the dust. You can actually see right through the dust with this telescope, and you see the bright center of the galaxy. This looks pretty, it's related to this, but it's pretty different. You can take the same instrument, you can get rid of all the visible light, and you can look at the background fluctuations that you can see in the microwave, and you get an image that looks like this. This is the COBE result. These are microwaves. This looks like random noise, and it is pretty random. The weird thing about this is that it tells you what the universe was like 200,000 years after the Big Bang. It's all kind of cool physics about the Big Bang and how matter started. And it's by looking at the sky with a new kind of instrument. Now, we've got yet another new kind of instrument, this gravitational wave detector. And here's what the night sky looks like there. We've got our one source down in the corner. It's on for about 200 milliseconds. So really I should turn the star off, but I just can't stand it. Just gotta leave it on, right? But what we're hoping to see is all kinds of new interesting astronomy. So this is a picture of a supernova that went off in 1987. The core of a supernova has a lot of mass, and it collapses all at once and drives one of the most powerful visible explosions in the universe. And as that mass collapses, we should be able to see that with LIGO and compare that to what the visible people are doing. This is the remnants of one of those supernovas. In 1054, there was a supernova in our galaxy. It was so bright you could see it in the daytime. Chinese astronomers wrote all about it. That's how we know it was in 1054. That thing collapsed into one of these neutron stars, these dense nuclear objects. And if that thing is perfectly round and spinning, we can't see it. But if it's got a little lump on it, a little wart sticking off one side, those warts weigh about as much as Mount Everest do. And if that wart is spinning around 60 times a second, same speed as the Crab pulsar is, right, we can see that mass moving around, and we can compare it to what the people doing the neutron stars can see. When two of those neutron stars crash into each other, you get a signal that looks like this, we think, on our observatory, and a giant burst of gamma rays that comes off. So we can look with the gravitational waves, compare those to the gamma rays, and learn a lot about these really energetic explosions called gamma ray bursts. There are other people doing gravitational wave astronomy. I have to do a shout out to all my colleagues. Here's LIGO. We can see stuff around 100 cycles a second. There's a group of folks doing LISA, which is a space-based version. Instead of being 4 kilometers long, their arms might be as long as 5 million kilometers long. Oh, am I out of time? Okay, all right, good. I'm almost done. So these guys can see stuff. We can watch with radio waves. So there's some stars out in the universe. Beep, 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 beep. They're very, very good timers. And if a gravitational wave passes between us and one of those stars, it'll actually stretch the space. And so the star will seem to move farther away from us and then closer again. And we can watch things like the centers of galaxies crashing into each other. Instead of 30 solar mass black holes, it'll be billion solar mass black holes. There might even be some gravitational waves distorting that initial view of the universe, that Kobe picture with the microwaves from 200,000 years past the Big Bang. Gravitational waves should distort that image as well. Maybe we can tell something about how the universe came into being. So, it's not the end of gravitational wave astronomy, it's just the beginning. But it is the end of my talk. So if you guys have questions, now would be a great time to begin the questions. Yes?